All right. So the first thing is, remember there's a quiz on Friday. Any questions about the quiz? And all right, so what I want to do now is I want to do a thing, have you do a thing where I set up a structure. If we ignore the weight, it's a truss. Then we'll put in the weight, and we'll sort of see how those internal loads relate to each other. Just sort of getting used to how all these different things kind of fit together with each other. Before I do that, anybody have any homework questions?
I don't think you signed the form.
Oh, okay. Okay, so let's say we have a structure like this. That's supposed to be symmetric. And each of the lengths are 2 meters. And the masses are each 10 kilograms. And applied at the pin here, we have 1,000 Newton force down and 1,000 Newton force to the left. And these two angles are 30 degrees. Okay, so we're going to do this 2 ways. First, we're going to neglect the weights. And we're going to calculate the internal loads. And draw the internal load diagrams. And then second, we're going to include the weights and do all that same stuff. If we neglect the weights of these members, you can see that, so there's no weights on the things. All of the external loads are applied at the pins. So everything's a 2-force member. So we can treat this as a truss, okay? In a truss, what do you expect to see for the internal loads? Yeah, exactly. So I guess just for comparison, we'll draw those, we'll draw all the different diagrams, but the only ones that are going to be non-zero are going to be the tension, okay? Then we're going to include the weights. That means you're going to have distributed loads, you're going to have to use rotation matrices. You'll get some differences, but the masses, you know, the weights here are going to come out to be about 100 newtons, so it's about 1/10 of the external loads. So we should see the relationships, see that they're kind of similar, but you know, the second thing we're going to do is going to be the accurate one. Anybody have any questions about what we're doing here? Okay. Well, let's call this body 1 and this body 2 A, B, C. And for part A, let's just go straight through all the way through to the diagrams because it's all pretty quick. So work together on this, talk to each other, talk to me if you have a question. And I'll just give you a little time to come up with these diagrams and then I'll do it and then we'll go on to the harder one. Okay?
So for the truss, we just start with.
So the fastest way to do this is just do a free body diagram of the pin B. We're going to treat member 1 like it's in tension, like it's a cable. Body 2 like it's a cable. Then we have a 1,000 Newton force that way and a 1,000 Newton force that way. So Newton's second law says the unit vector for that force F1 is negative 0.866, positive 0.5. That's like cosine and sine of 150 degrees. Unit vector for F2 is positive 0.866, positive 0.5. I'm going to treat these like a single force, so we have negative 1,000 in the x direction, negative 1,000 in the y direction. So negative 0.866 F1 plus 0.866 F2 is equal to 1,000. And 0.5 F1 plus 0.5 F2 is equal to 1,000. So from equation 1, I'll call this 1 and this 2. From equation 1, we can see that F2 is equal to F1 plus 1154.73. Plug that into equation 2. We got 0.5 F1 plus 0.5 times the quantity F1 plus 1154.73 is equal to 1,000. And so we get F1 plus 577.37 is equal to 1,000. So F1 is 422.63. That's, yep.
Do you use 1 meter for the length?
Oh, you don't need to know the length for this. You only need the direction of that force. So that's what we know, that the magnitude of, say this F1, we know the magnitude is F1. So we just want to multiply it by a unit vector in that direction. So I just use cosine and sine.
Okay.
Yep. And then F2 1577.37. Okay, so for member 1, if we draw these diagrams, we're at 422. And then the other two are just zeros the whole way. Okay. And for member 2, we're at 1577, and then these two are 0. I'm just drawing these so we can compare all these diagrams after we do the next part. Okay, so these members are both in tension. Nothing else is going on. Anybody have any questions about that calculation? Okay, so now for part B, now it gets more complicated. Yeah.
I have a quick question. So even though the force vectors are like pointing into the, like if you go back to the pin, like F2 is pointing into the member, that's in tension?
Yeah, so I think the way to not get confused about that is to think the way you're doing this is if those members are cables. The only difference between this and a cable is if you get a negative answer, you're okay with it. Okay, but remember, so, yeah, so
Good question.
if the reason it looks like it's going into the member is because we're not isolating the member. Like we're isolating that pin. If we isolated the member,
So it's a reaction between the pin and the member, which is then.
yeah, it's a Newton's third law thing. You know, if we isolated the member, we would get forces like that.
Okay. Because it makes sense to me looking at the actual like flow thing that
Yeah.
both members are in tension because
Right.
both forces are pulling away.
Yeah,
But,
right.
So, okay.
Uh-huh. And yeah, so the reason that it looks like it's going into the member is because we're not looking at the member, you know. If we isolated the member, it would be in tension pulling away from both sides.
So when we're doing the truss simplification, we don't consider the pin to be a part of.
That's right. That's right. We're just isolating the pin on its own.
So the same goes for F1. You get the Newton's third law.
Right.
reaction.
Yes, because what I drew here was the force on the pin by the member. And so then the force on the member by the pin would be the opposite direction.
Okay, but we don't have to flip the sign for the internal load.
Well, no, because, I mean, we figured out that, so we treated it like a cable. We figured out that in both of these cases, they're actually acting like cables. What that means is, I mean, when you actually have cables, we never draw free body diagrams of the cable, but what they would look like is this. And so that's what we have here. And then if you did, so if you did a free body diagram, like did a cut for a cable, you'd have a force going this way of 477 or whatever. Then you'd have your internal loads. V and M would be 0, but that T would have to be equal to that 477.
Is it true to say, like, the F1 we calculated, then there's the Newton's third law, which reverses the direction, and then the tension counteracts that force?
No. Uh, so just, I think it's over as soon as you say the Newton's third law part, you know. We know that we figured out that the force on the pin by F2 is this direction. So we've also figured out that the force on member 2 by the pin is the opposite direction. And that's really the end of it. And of course, you could do the full method for this and then go through the internal loads calculations and you'd get this same thing. Any other questions about it? Is it still sort of confusing and you're, yeah,
It's
kind of?
fine.
Yeah.
Close enough.
Yeah. Okay. Come on. All right, so now for part B, this is going to be more involved. We're going to, first calculate the external loads on each member. Then we're going to transform the coordinate system using the rotation matrix. And then we're going to calculate the internal loads. So start with this one and calculate those external loads on every one of the members. And then when you're done with the calculations, put them in a free body diagram of each member. So any forces that act at the same spot, you can combine those.
What were the weights again?
So my free body diagrams that I did my calculations from, there's an RA there. There's a weight force at the middle of 98.1. There's a force F12, and then there's the two applied forces. And then for the other body, there's RC, the weight, and negative F12. And from the calculations, I got RA is equal to negative 450.96, 309.42. F12 is 1450.95, 788.68. And RC is 1450.95, 886.78. And when I put those back into the free body diagrams, we have a force up here of negative 450.96, positive 309.42. A force down here, now I'm adding up the F12 and these two 1,000 Newton forces. 450.95, negative 211.32. And then we have a downward distributed load of, the whole thing has a length of 2 meters. So this is 98.1 divided by 2. So 49.05 newtons per meter. And then on the other one, at the joint C, 1450.95, 886.78. Down here we have negative F12, so negative 1450.95, negative 788.68. And then the same downward distributed load of 49.05 newtons per meter.
So you need the distributed load to point into the rotation.
Yes, that's right.
You can't do it with force.
You cannot do it with point force. If you did it with a point force, you'd get kind of like an approximation. It would kind of make some sense, but this is the way to do it. So if you didn't finish doing this calculation and you want to finish and check your work, you can check it against this. But on Friday, we're going to use the rotation matrices and calculate the internal loads and then compare to our approximate internal loads from the trusses. Okay? All right. So we got to go to the other room now.